Imaginary numbers are called imaginary numbers because they're not real numbers. Okay? It doesn't mean they're fake. It doesn't mean that they don't exist. We study imaginary numbers primarily. Why? Any guesses why we need imaginary numbers, or where they come from, or what they apply to? If you have the square root of a negative, yes. But they also help us with our big deal thing that we talked about day one of class. Anybody remember what we talked about day one of class? They help us complete the solutions to polynomial equations, right? So if we have a fifth degree polynomial equation, we need 5 solutions. And oftentimes those solutions won't be real numbers, they'll be imaginary numbers. So it's the field of numbers that kind of completes all of our solution sets for these fifth degree polynomials. Now, there are some actual practical applications of complex numbers, singularities they're called, and now we're getting into theoretical physics and black holes and things like that. Then there are some actual applications of real life applications of imaginary numbers. Okay, so it's an important deal. This is an old branch of mathematics. Galileo Galilei, right? It was 1564 to 1642. He was kind of the groundbreaker of imaginary numbers. So it's old. This is old math. This is kind of, the calculus was coming of age at the same time. As a matter of fact, Sir Isaac Newton was another guy. Y'all have heard of him, right? He was dashing. I wonder why his right eye is so much bigger than his left. It happens, I guess. But that's Sir Isaac Newton. What's he famous for? What's Isaac Newton most famous for? Science. Which science? Physics. Physics, which is an applied math class, right? It's really math.
The apple thing.
The apple thing, right? He formulated a lot of the physics behind gravity, laws of gravity, laws of dynamics. An object at rest stays at rest unless it's acted on. Equal and opposite reactions. For every action, there's an equal or opposite reaction. So those laws that govern the physical universe, Isaac Newton was the one that kind of really formulated those and theorized them and proved them, but he was also a groundbreaker in this imaginary number stuff. So it's not new math. There's no common core here. We use it for this. And you guys know this because you had it in Algebra 2 at least, if not some mentions of it even in Algebra 1. What is the square root of negative 9? 3i. Why is it 3i? Where does the I, that looks like a 6, doesn't it? Where does the I come from? It's an upside down check mark. Do what?
There's letters involved?
There's letters involved. Where does I come from, and what is I? What is I? I should say, what am I? What is I in the grand scheme of things? All right. I is equal to. All right, the square root of negative 1. Okay, so that's where it comes from, the square root of negative 1. I always forget about that happening in this lesson until I'm actually teaching this lesson. I is the square root of negative 1. I is called the imaginary unit. Okay, the imaginary unit. It's 1 in the imaginary side of things. Okay. So I is equal to the square root of negative 1. So where this comes from is we take it from yesterday. The square root of negative 9 is the square root of negative 1 times the square root of 9. So we can break it up into its imaginary part and its real part, inside. So the square root of negative 1 is I, and the square root of 9 is 3. And that's where we get the 3i from. All right. So we've got 3i there. Now, this is important because when we're dealing with imaginary numbers, we've got to know that the rules are different. Okay? The rules for working with imaginary numbers are different than the rules for working with real numbers. All right? Is everybody okay with that? For example, and I want you to see this clearly because we're going to come into something in just a second where we'll use it. Let me just blank this out and go here. If we have the square root of 6 times the square root of 5, what does that equal to? Square root of 30, right? If I have the square root of negative 6 times the square root of negative 5, does that equal to the square root of 30? If we're just following our normal rules, then the answer would be yes, right? Okay, but the answer is no. It's not. They're not equal to each other. All right, and that's because the rules that govern complex numbers, imaginary numbers, are different than the rules that govern real numbers. Okay, we multiply them differently and we divide them differently. Thankfully, they add and subtract the same, but the rules for multiplying complex numbers are different than the rules for multiplying real numbers. In the complex plane, in the imaginary numbers, a negative times a negative is not positive. Okay? So how you have to do this, let me show you how you would have to do this, and let's go to something that's a little bit more easy to work with. Let's do two things that are easy to work with here. Square root of negative 9 times the square root of negative 16. Now, we can't multiply negative 9 times negative 16 and get positive 144 and say that's equal to 12. It's against the rules. You can't multiply complex numbers like that. Okay? So everything inside you wants to, but you can't. As soon as you notice that you're working with imaginary numbers, then the way we approach the imaginary numbers have to change. So we have to deal with the negative part first before we can do the multiplication. All right? So the square root of negative 9 is 3i. And the square root of negative 16 is 4i. And 3i times 4i is 12i squared. That's what we want it to be, right? And that's what it is. We're still going to add exponents. And what's the value of I squared?
Negative
1. I squared is negative 1. And so this is equal to negative 12. Okay? So we have in the complex world, we can't just do what we've always wanted to do and multiply negative times negative and get a positive. It doesn't work that way. In the complex world, you have to deal with the negative, the square root of negative 1. You have to deal with the imaginary unit before you can do anything else. Now, we flew right past it. Why is I squared equal to negative 1? Right, because the square root of negative 1 equals I. And if I square both sides here, what do I get?
Negative 1.
I squared equals negative 1. All right. So there's another misnomer, right? It's another contradiction. If you square a real number, the answer is always what? Positive. If you square an imaginary number, not necessarily going to be the case. Okay, so it's one of those things where we have to kind of readjust our thinking about the way the numbers work. We're going to graph them differently when we get to trig. We're going to graph complex numbers. So we're going to do a lot of things that are different that you've not done before with complex numbers. Okay, so let's go to back to this and have a look at square root of negative 16. We just did that one in the context of that other problem. What's the square root of negative 16? 4i, all right? And the square root of, so then we looked at I squared already. What is I squared?
-1.
It's equal to -1. Okay, because square root of -1 times the square root of -1 is just -1. So getting a little bit more complicated here. These two complex numbers, guys, we'll talk about this well, let's talk about it now. Let's talk about standard form of a quadratic number. Did I just say quadratic number? Standard form of an imaginary number is a plus bi. We'll do this so much in trig and the last part of trig that you'll just get almost, sick of complex number stuff. But one of the great applications of trig is that trig gives us some really neat ways to do powers and roots of complex numbers that algebra is a little deficient in. Okay, a plus bi is standard form for an imaginary number, a complex number, where a is the real component of the number and bi is the imaginary component. So complex numbers, the standard form for a complex number is a plus bi. Okay, and a complex number is not considered simplified unless it is in that form, a plus bi. Your answer has to be like that or it's not simplified. Now, a or b can be 0. If a is equal to 0, then we have what's called a purely imaginary number. It doesn't have a real component. If b is equal to 0, then we have what's called a pure real number. It does not have an imaginary component. All right, and when we graph imaginary numbers and do things in the graph in the complex plane, and you'll kind of see that there's something special about those purely real numbers or purely imaginary numbers. Kyle Pieringer is online. Yeah. All right, I'm gonna have to turn that off. So we're going to FOIL this exactly like we would normally work with an algebraic expression. Everything's the same. So we're going to multiply 3 times 4, and that's going to give us 12. 3 times negative I would give us negative 3i. 2i times 4 gives us 8i. 2i times negative I is negative 2i squared. And y'all remember doing this very vividly, I think. Now what do we do with the I squared? You make it a -1, which is going to turn that negative 2i squared into positive 2. And when it turns into positive 2, we can combine it with 12. And that's going to be 14 plus 5i. And that is the reason, that is the way we want our answers to look. And we want our answers to look that way because that is standard form for a complex number. What's the real component of this complex number? 14. And the imaginary component is 5i, right? Or you could even say it's just 5. 5 is the imaginary component. So we're going to have all kind of applications of that when we get into trig with vectors and that sort of stuff. So 2 minus 3i squared. What is this telling us to do? It's telling us to multiply 2 minus 3i times 2 minus 3i, right? So we're going to use our distributive property, the FOIL method, if you will, and we're going to multiply these two numbers together. Two times 2 is 4. Negative 3i times 2 is negative 6i. We got 2 of those. And then plus 9i squared. And the I squared is going to become -1, which makes that -9. And we will get -5 minus 12i. All right? Easy, right? Okay, good. I thought this was a better lesson for today than the other lesson I initially planned to do today. 4 minus 3i times 4 plus 3i. Now, what do we have here? What's the relationship of these two numbers? What's the relationship between these two numbers? Why am I calling it two numbers? Why am I calling these two numbers? Here's a number and here's a number. Is this a binomial? No, it's one complex number, right? It's not a binomial. The rules kind of apply, multiplying binomials, but that's not a binomial. It's not two terms. It's one number. We are not, y'all listen to me carefully, we are not manipulating variables here. I is not a variable. We're multiplying two complex numbers, and that's an important distinction to make. Okay? These are two numbers. These are not two expressions. I have an a plus bi here, and I have an a plus bi here. Those are two complex numbers that we're multiplying times each other. All right? Zach, what'd you say? What are these called? They're called conjugates. And when we multiplied conjugates earlier with algebraic expressions, we ended up with difference of squares. And I told you that something special always happens in mathematics when you multiply a number by its conjugate. And if we multiply a complex number by its conjugate, what do we end up getting? One what kind of number? One real number. And that's special, right? If we multiply a complex number times its conjugate, we get a real number. Completely over in a different part of the number system. Okay, so conjugates are very important in complex number theory. So we'll distribute here. We're expecting that middle term, so to speak, or the imaginary components here are going to cancel each other out, and all we're going to be left with is real components. And if you multiply an imaginary number by its conjugate, you're always going to get a real number. Okay? That's huge, and we're going to use that tomorrow when we're rationalizing denominators. Rationalizing denominators, we're going to need this conjugate thing. All right, we're getting close to done. We're going to do this one and maybe one or two more, and then we'll be finished for the day. And y'all see why I don't think you need to practice this much. Yeah, I mean, this is something that we can, it's fairly easy to do. And I'm going to give you some problems that you can look at if you want to, but it's not going to be required for homework tonight. What's different about this problem, and why do you have to be careful? There's an addition sign between these two complex numbers, so we are going to add them instead of multiplying. And somebody on every test, that when I roll around and throw a problem like this in, somebody almost inevitably multiplies the two numbers instead of adding the two numbers. But the way we add complex numbers is we add their real parts and we add their imaginary parts, and that's it. It happens. It works just like you're adding an algebraic expression, but keep in mind this is not an algebraic expression. This is two numbers. This is one number here, and this is one number there. The complex numbers in standard form. So what do I get when I add these two together? 7 plus 4i is correct. Now, the practice sets have some problems that look a little bit more complicated. But no matter how complicated the practice problems get, ultimately every answer is going to end up being in standard form. So our ultimate goal, if we're working with complex numbers, is to get something that looks like that every single time. If it doesn't look like that, then it's not simplified. So when you see the directions to simplify a complex expression, that means they want you to put it in standard form. Okay, because we need to know the real component and we need to know the imaginary component so we can graph it, so we can do write it in polar form, a lot of the things that we'll be doing later in trigonometry. So a plus bi is standard form. So let me give you this. Let's do 6 times 3 plus 4i minus 3i times 2 minus 6i plus 4i. So this is a little bit more complicated process involving complex numbers and values, and it works exactly the way we would want it to work. 6 times 3 is 18. 6 times 4 is 24i. Negative 3i times 2 is negative 6i. Keep in mind that this is negative 3i times negative 6i, which makes it positive 18i squared, plus 4i hanging out here on the end. Now I have to make a substitution for I squared. What is I squared? Negative 1. All right, so that's going to be negative 1. I'm going to do this kind of there, which is going to make that value negative 18, right? So 18 and negative 18, no mas. No mas 18. Okay. 24 minus 6 is 18, and 18 plus 4 is 22i. Now, it would be okay if you wanted to write this as 0 plus 22i. It's not required, but we always need to be reminded that standard form for a complex number is the real part plus the imaginary part, right? So if we end up with a purely imaginary number, that means the real part is 0. And we need that for graphing this complex number. Did y'all do any graphing of complex numbers? Okay. It's really easy. Graphing complex numbers is simple. Now, if you want to have a look at some practice problems, you can, but I don't think you need to. We can look at them tomorrow. This is not an assigned deal. It would be page 135. One through 20. Just have a look at those. Like I said, this is not required homework, and I don't think you need to do homework on this assignment. I wouldn't check it if I did assign it. I think it's that easy, and you should know it, right? This would be one that would be optional. So tomorrow we'll do rationalizing denominators.